maybe the second part requires some thinking, so maybe it's good that you just look at it and then maybe at 4 you can quickly fill it in and you have thought about it. You have one? You have one? Huh? Oh, you need some more. Sorry. Okay. So the first bit is easy. The second bit requires some thinking. Do you want to do it now, and do you have 5 minutes to fill it in, or do you want to do it at 4 o'clock? 4 o'clock. Okay. Okay. So we continue here, and you do. Good. So catalysis. Catalysis is interesting because it started actually with Wolfgang Hermann in Munich, who used this ruthenium-carbene complex, but he put a carbene on top and a carbene on the bottom, and looked at this for catalysis, and he looked as well at some carbene palladium acetates for cross-coupling. That's in the mid-90s this happened, and he could show some efficiency, and especially now in cross-coupling, the bis carbene system was totally ineffective, or almost ineffective, not very good. But then in cross-coupling, he could show that many of his palladium-carbene complexes were better than the phosphine complexes. So he is the father of the superphosphine terminology. He had this thing of, oh, but carbenes are better than phosphines, so these are superligands. Only in cross-metathesis this didn't work very well. And then one of the first ones to join that field was Steve Nolan, who picked up on this superphosphine terminology and basically took each and every catalyst that was out there in the literature, replaced the phosphine for a carbene, and wrote a paper how much better the carbene now is. Sometimes this was totally right, sometimes he forgot to mention what is worse, because there was, like everywhere in life, you have some pleasure, but then also there's one or the other disadvantage. Okay, that's the same with carbenes. Not everything goes well. So he, unfortunately, his career ended a bit in a mess, and at the moment he's looking for a job. So if you have one, here's a prominent chemist that you could employ. But if you know the full story, you'll probably be happy to just keep your hands safe and dry and clean. And anyway, there's been huge variations, but you'd see, so this is the classic domain of phosphine catalysis, and that's really implied by the whole idea of carbenes are better catalysts than phosphines. And then people started to move further. This should have been a hybrid catalyst, so that's a polyoxymetallate that is immobilized with a carbene. Cavell has pioneered this ring expanded systems, 5, 6, so rather than 5 rings here, he used 6, 7, and 8 rings to make carbenes. These are very interesting because with the expansion of the ring, this angle becomes much larger. And we've seen in the very first slide that the larger the angle is, the more we go to a singlet carbene. So the donor properties change, the pi acceptor, pi donor properties change, and you get a new reactivities. Then we had some asymmetric systems. Asymmetric catalysis with carbenes is very delicate because you have to be very careful about how you insert your metal center, or what is your structure of your ligand. In these type of systems, you have to be adamant that you don't use silver oxide and the transmetallation route. Why? You have a very acidic proton here that may be thermodynamically stable enough to stay there, but kinetically it may get deprotonated and reprotonate. Consequence, you destroy your chiral center, you racemize. So we've seen this with a number of examples where you have a proton adjacent to the heterocycle. Silver oxide actually does a thing that we usually don't observe. It deprotonates and reprotonates. It has zero effect if this is a CH2 group, but it has a significant effect if you have their chiral information stored. You delete it in the methylation step. Metathesis became only fruitful when Grobbs discovered a complex where you have only one phosphine replaced by a carbene and not the other one. There's another story to tell, well actually two, because Steve Nolan published almost the same compound, almost the same time. If you look at the submission dates, you find out that actually Nolan submitted like 3 months before Grobbs submitted. If you look at the papers, you find that Grobbs cites the unpublished work of Steve Nolan. So you count 1 and 1 together and you understand who was the referee of Steve Nolan's JAGS paper. And then you wonder, why does Bob Grobbs get away with this? Maybe he's just a big name, so everybody trusts him nonetheless. Maybe it has to do with some of the ethics in the system there, that some guy had the idea, some other guy took it, tried to publish it, and then there was a bit of a... Anyway, important feature in the carbene case is that I think we lose here. That's probably the problem of the PDF. You know, there's almost no metal center there. Well, there's a bit. So the important step in the Grobbs catalysis is that, oh, here it is. That you have two important steps in getting metathesis to work. First, one ligand has to dissociate to give room for the olefin to coordinate, so that's the catalyst activation. And then the olefin has to coordinate. So you have a two-step process. This is dissociative. Turns out you understand trans influences, trans effects. Carbene has a high trans effect, phosphine has a lower trans effect, so you expect that the phosphine dissociates easier when this is a carbene than when this is a phosphine. You look at the rates, K1, which is the phosphine dissociation, for a phosphine about 100 compared to the carbene. What does it mean? The phosphine accelerates phosphine dissociation. So the trans effect is here not at play, there are other factors at play. So if you see this, K1, 100 times larger for the phosphine, we know that catalyst activation is 100 times faster in Grobbs 1 than in the carbene analog. So why is the Grobbs catalyst much better, the second generation? Because the second step is highly reversible in the phosphine. Look at that. The K2 to K-1, so this one here, the back bonding is 1,000 times faster than the olefin binding for phosphines. So it's the phosphine that does not stabilize this intermediate. It facilitates the formation of it, but it's 1,000 times faster rebinding. While with the carbene complex, so if you have the IMES here, the dehydrogenated IMES, this step is relatively slow, but then this one is comparably fast. So it's equal rates, if you like, for going back and forward, while this one goes 1,000 times faster back. Or if you like, once you have this compound with the carbene, 1,000 times faster, you have the olefin binding and you start cycling. So it's not the phosphine dissociation that's accelerated, but the olefin coordination. Can we understand this? Olefins are back bonding, so they need a strong trans ligand, so the carbene helps. So maybe I don't dwell too much on olefin metathesis. A huge step forward was Pepsi catalysis in cross-coupling. So Palladium catalyzed cross-coupling has gained significant momentum with carbene. So Greg Fu, who was a hallmark in phosphine discovery, maybe 8 years later, Mike Horgan and then as well Steve Nolan developed these, well Mike Horgan in particular developed these Pepsi type catalysts. Pepsi stands for pyridine enhanced precatalyst, preparation, stabilization and initiation. And the bottom line here is that you add a pyridyl ligand as a throwaway ligand that very easily dissociates, so you have a very facile pathway to activate the catalyst. It doesn't need to be the 3-chloropyridine, as well normal pyridines do the job, imidazoles do the job, any N-heterocycle is useful for this. You have to be a bit careful because not all Pepsi catalysts work reproducibly well. You have to be a bit careful with the conditions and how you operate the system. But the concept is pretty nice. You have an easy dissociable ligand, then you get the reductive elimination, and you can couple then a huge variety of systems. Now, about 2 years ago, he published a second generation of Pepsi catalysts, which don't have these isopropyl or mesotyl substituents, but have here isopentyl substituents. So they're much larger, and isoheptyl or substituents. So here much more bulk, that puts more pressure on the chloride ions, so you have more easier reductive elimination and access to the palladium zero as the catalytic active species. And you'd see the system is then sterically not so packed. You can couple very bulky substituents, diorthosubstituted boronic acids, orthosubstituted phenyl groups as substrates. That works very powerfully. Book called Hartwig amination, the whole field has been done. Hydrosylation, extremely efficient, but then again, EEs are a bit mediocre, and that has to do in and out with the lability of the CH. So we think this is the key feature, that enantiomeric excess in these reactions is limited. There have been reactions where with very high EE, Kevin Burgess has done a good job there in developing systems. In many of those cases, the chirality is at different places, like in a binap substitution or so you have a different type of chirality. Or you're absolutely clean that you don't have any basic or acidic environments that could racemize these benzylic positions. Transfer hydrogenation we discussed already. We've seen that complex in one of the previous slides. There are others, maybe not that quick, but others that are doing the job very nicely. This is with isopropanol. You have wonderful systems with formic acid, so carbines play there a good role in transfer hydrogenation. We already seen this hydrogen borrowing, which is a system from Mike Whittlesey, where cyclomethylation is reversible and you can store dihydrogen. And we talked about cascades. So the field is extremely large for carbene chemistry, and this is a slide I think I packed in about 3-4 years ago. I think I would totally need to overhaul it, but there's no catalytic reaction, I'd say, that hasn't been tested with carbenes. Hydrogenations, oxidations, couplings, metathesis, you name it, carbenes have played a role. People have looked at iridium systems for alkane dehydrogenation with extremely moderate success. Turnover numbers of 10. So there is still room. But then one thing that we've seen with hydrogenations also is that we have to be careful how we arrange the metal and the ligand. Because a common deactivation pathway, which may also play a role in cross-coupling, it's what I've shown you very early on. Maybe you still remember. So this is the lowest, this is the carbene low orbital. This is the second, the middle orbital, you see. No coefficient on the carbon, no pi interactions. So that's the empty orbital, that's the LUMO on the carbene. and the HOMO is then, of course, and it's this HOMO orbital where the hydride can shift in, where the 2 electrons can fill in this empty, so this one here is filled. So there are 2 electrons in here, so this is the lowest, this is the middle, this is the upper one. So in this orbital, the hydride can move over. The consequence is that the metal-carbon bond is broken, so we have a decomposition pathway for hydrogenations. And as a consequence, in direct hydrogenation, you have to engineer your carbene in such a way that it cannot do that decomposition. Chelation is one of the classics. So with the chelation, you can fix the orientation of your carbene with respect to the metal coordination plane, and so you can prevent to a large extent the reductive elimination of the imidazolium salt. Does not work always. Maybe you remember that palladium carbene story I showed you very early on about heterogenization of a homogeneous carbene catalyst. There it didn't work at all. So that's the problem of hydrogenations. Also, hydroformulations may suffer from this, because there as well you have a high pressure of dihydrogen. Carbonylations have been shown, so there's alkane hydrogenation. Polymerizations. Polymerizations is still an infancy field. Some polymerizations have been shown to work with carbenes. There's a huge area that still remains to be discovered. Very little has been done. Cross couplings, we've seen all types, HD exchanges, oxidations, there especially Matt Sigman and Shannon Stahl have made wonderful contributions for alcohol oxidations in the early days. Now a few groups, including some in India, very close by, have picked this up and pushed it further. A very interesting application are the semi-hydrogenation catalysts, and there in particular Kees Elsevier in the Netherlands has had a prototypical example. I've seen some this week again. We have some in our house as well. And you'd see a large field of chemistry that has more of this type of chemistry. You add an imidazolium salt, you add a bit of base, you add a metal precursor, and woof, you see fantastic chemistry. Me personally, but that's my very, very personal approach to this, I don't like this too much, because we never know what's really happening. So I prefer to go as close as possible to the active state of the catalyst. So I prefer to pre-synthesize the complex, then go. I know we will miss out for a few things, because if you put the cocktail together, the system may assemble to the most active state. While when we pre-assemble it, we directed it already one direction or the other. So there's the balance. But at least we think we know a bit more what's happening. We know a bit more. So that's on the hydrogenation. I probably skipped this. What do we know more? So a classic of this shipping things together has been this cocktail for cross-coupling. Works very well. Again, you wonder, what is the palladium acetate doing? What is the carbonate doing? Is the carbene, and they could show that if you leave the carbene away, that actually the catalytic activity is not so high. Now you have a number of events there. For example, palladium nanoparticles are stabilized by N+ charges. You have an N+ charge, you have a cocktail for making palladium nanoparticles, could be very active. So does this prove that this is a carbene catalysis? No. Could be, but no proof. What else? Some guys have used this and looked first what you get. What did they find? That with some systems, you get the complex that you probably would expect. Now, this is a poor throwaway ligand. You have to push some energy in to get into the Nolan type or organ type system. Depending on the R group, you also form this. That's a different compound. So if you start with one or the other, you know at least which one is catalytically active. Now for this one here, you need to consider now subtly two things. This one here is a stronger donor, so that bond should be weaker, or that ligand should, no. That is a stronger donor, so the trans effect should be higher. That may labilize that compound. The bond strength seems to be higher for this compound, so dissociation of that guy should be easier. So now we have to test the whole thing. And it turns out that if you add here a reductive elimination agent, this guy eliminates preferably over this one. Could be that this is purely steric, because of course here you have an easier access route, while here you have two ortho substituents. Could be that it's electronic. Anyway, these abnormal carbenes, so that's maybe a thing to, we still have 5 minutes. That can be very interesting from a number of points of views. First, they are stronger donors, and you'd see this from the pKa. Second, they can still be made carbenes, and Guy Bertrand showed this in a crystal structure. So here's the crystal structure of an abnormal carbene. You can maybe barely see. I should have colored this. There's one nitrogen, there's the other nitrogen, there's no substituent here. But you have to, in order to stabilize this free carbene, and that tells you again how labile all the substituents can be, he had to extensively substitute the ring, phenyl groups on the carbon, disopropyl aryl groups on the two nitrogens, so no alpha CH protons, otherwise the system doesn't form. He had to be careful if he used a lithium base, you don't form the free carbene, but you form the lithium adduct. And that we've seen with a number of other carbenes. Lithium bases don't form the free carbene, but the lithium carbene. For synthesis, this is not so tragic, because you do a transmetallation rather than a metallation, so it still goes. But if you're interested in the free carbene, potassium is your choice. With potassium bases, you form the free carbene, the potassium doesn't form the carbene bond. Then he could add CO2 to form this guy, gold to form this guy, and there's your man Mandal, country fellow of yours, who then started to look at palladium and copper compounds of that sim. Not much else has been done with this compound, largely because it's so bulky and it's a tedious operation to get there. So either you spend some months to make it, then you have it, and then you exploit it, or you say, I make a simpler thing. And then it's very bulky, so you can't do too much chemistry around that carbene. While with others, you can do much more chemistry. So here's another route to make these abnormal carbenes, oxidative addition. You can easily functionalize this imidazole on the C4 position. Easily means 2 days. First you iodinate all 3 positions, then you bleach 2 out, and you keep selectively the third one, so it's not really an atom economic, but who cares, in 2 days you have the compound, so it's not an industrial scale thing, you want the compound. Then you can selectively manipulate first this nitrogen, because the iodide is protecting that nitrogen, so you can put in first a wingtip group here, and then a chelating group or another wingtip group here, then you can use oxidative addition chemistry to make the abnormal chymie. Other approach, CH activation. If you do CH activation, you have to make sure that your more acidic proton is absent. So you alkylate or arylate this system here, and you make these 2C2 alkylated imidazolium salts. Then you can cyclometallate or just metallate with palladium acetate. That works. Here we are selective. We get selectively this compound here. So we think there's an umbrella effect, that the palladium is first attracted by the positive charges of the carbene, and that actually triggers metallation of the inner CH bond rather than the outer CH bonds. That's the closest we could come up with as a result, because electronically this CH group and this CH group should be about the same. So we should not have too much of this compound. We should as well have lots of polymer and bromine. So we thought we can maybe analyze the properties of these abnormal carbenes, but if you look at these compounds here, of course the steric influence plays a role. And we can see this especially when we look here in the halide region, and these methyl groups, these alkyl groups, they're totally different here from here. So if we compare those two guys here, we don't really compare likes with likes. So as a consequence, we synthesized two compounds that have exactly the same steric environment. Methyl groups all over the place. And with this, now we can compare the two, because you can take this ChemDraw, shift it over, and you see it's an exact match. You can take the crystal structure, shift it over, and you see it's almost exactly the same. Slight deviations. The deviations that we see are in the palladium chloride bond. So they're shorter here than here. This is the abnormal carbene. That's what we expect from a stronger donor. A stronger donor should have a larger trans influence, so the chloride should be further away. With iodides, we don't see this. If this is an iodide, then the methyl groups become repulsive. So then steric interactions make the iodide metal distance the same in both compounds, because the iodide is too big. So with small ligands we see the difference, because then there's no steric interference. So the synthesis was not too trivial, but it worked out in not too much of a time, but then you can compare. And then we can as well compare the properties of the metal center. Now palladium is not so good for redox chemistry, because the palladium 2 state is too stable, but you can do photoelectron spectroscopy. What you do there, you put this under high vacuum, and then you ionize it, and you see how strong are the d electrons bound to the core. And this gives you an idea of how electron-rich the metal center is. And you see this abnormal or non-classic or mesionic carbene, there's a shift of about 0.5 electron volts. What's 0.5 electron volts? Is this a lot? Is this little? Is this something? An electron volt is an oxidation state. So if we have a 2 electron volt difference, that means we have a difference of 2 oxidation states. So what we have here is we have moved half an electron volt to less tight bonding of the d electrons. So easier mobility, higher electron density, more electron rich. So then the d electrons become more mobile, so less binding energy. So half an oxidation state, that's like between 2 to 1.5. I thought this is significant, but I didn't know what to do with it. So then we looked at how we can abstract the chlorides, and then suddenly we knew what to do with it. Because when we run this reaction, the classic thing is that with silver BF4, you abstract the halide, you make silver chlorides, and you get your coordinating solvent there, and you have the cationic species. Now, because the palladium is so electron rich in this system, this is not the only reaction, but in fact the palladium is nucleophilic and binds to the silver. So we get this adduct. So that tells you what the palladium has changed to. You know, we discussed 2-3 times that palladium is electrophilic. Now in this case here, palladium is a base. It's nucleophilic. The palladium donates electron density to the silver. How do we know it donates? We know from crystal structure we get an interaction. We see that the silver is not exactly on top of the palladium, but it's actually leaning somewhere in this triangle, palladium, carbon, carbon. And computation actually showed that here is the HOMO that can donate electron density, and that's a carbon-carbon palladium molecular orbital. Here the same, and they can donate in the silver d orbitals. So again, it's a palladium to silver, or a CC palladium to silver donation. Now there's another subtlety that we see from this calculation, that is that in these abnormal carbines, we keep more or less such an electron distribution. We have a double bond that is now not localized because it's basically distributed over the metal, so we have like a metallo-allele type interaction and a NCN cationic fragment. And you'll be surprised how often we came back to exactly that notion. For example, if metal is iridium and we expose this to deuterated acids, we see selective incorporation of deuterium here. And if you believe in this resonance structure, it totally makes sense. If this is an allele anion, a D plus attacks either here or here. This one is not productive, you just remove the proton again. But this one here forms this type of intermediate. You get rearomatization and either this proton or this deuterium gets expelled again. So if you do this in excess of acid, you only see the deuterated compound. And that's what we see. In related triazole chemistry, the effect of this R group is much smaller compared to the effect of this R group. So again, we have this all seems to point, and while we don't have a total experimental proof, our experience indicates that there is much more of this olefinic character, of this metallo-allele character than aromatic character in the whole heterocycle. And that brings me back to what I showed you very early on with the resonance structures we had there. That I think in most of those compounds, actually, whether the carbene is here or whether the carbene is there, there's more localization of the pi interactions than not. So this pi interaction here is maybe it's not absent, but it's weaker than the other two. So this pi interaction is much stronger, this pi interaction is much stronger. But that's why also I think it's important to draw those pi electrons. They are relevant. They add to the stability, they add to the reactivity. So what do you do? First, we didn't know about this, so we used these type of complexes for cross-coupling. And of course, they couldn't be any lousier. You know, they were rocks. They didn't do any cross-coupling. Now, at some point, we thought we should write a paper, because you can take any palladium dust from anywhere, and for sure you get cross-coupling. you know, you open the literature and oh my God, if you have nothing that works, add palladium and do cross-coupling, for sure it works. Does it work well? No, but at least something works. So we thought maybe we should write a paper here. We have one of the rare palladium complexes that does nothing. But of course, this is hard to convince journals and referees that this is actually an achievement. So at the beginning we were frustrated, then we saw that actually what is the reason? The reason is that palladium-2 needs to be electrophilic to get into the catalytic cycle. Our palladium is nucleophilic. It does not want to reductively eliminate. Plus there are two cis-coordinating chelates which have a bite angle of about 80 degrees, totally unspectacular for palladium-0 stabilization. Not useful at all. So instead, we have a nucleophilic palladium. What can we do with nucleophilic palladium? Oxidative additions. So we can do chemistry that maybe other palladiums can't do because we can oxidatively add. So we tested this with a very harsh oxidizing agent, chlorine, which oxidizes almost everything. You'd be surprised, the normal carbene, no reaction. Maybe it does oxidatively add, but it reductively eliminates the chlorine again, which is not so likely because chlorine production is totally unfavored. But this guy here, in no time, first we thought we had the palladium-4 complex because we saw significant shifts in the ligand, but then crystallization and mass spectrometry showed that we actually had not the palladium tetrachloride bound to the two carbenes, but two chlorosubstituents. So we had an oxidative addition likely to make the palladium, oh, there's a class, is there at 4? Ah, so you're just late for the course, is it? Ah, not too late. So that's after 5 days and 4 hours. Okay, so we have oxidative addition, reductive elimination, that forms the chloro compound. Interestingly, this only reductively eliminates the chloro-carbon bond when we have these methyl groups here. When we don't have methyl groups here, then the carbenes become more flexible, and in the oxidative addition intermediate, the carbenes can come close together. So they can come closer together and you get a carbon-carbon reductive elimination. And you form this tricyclic system which has very strained carbon-carbon-carbons. I should stop. So here you see this is like 150 or 155 degree bond angle for an sp2 carbon that likes to have 120 degrees. So this may be useful for other chemistry, but we didn't explore this much because we never had it in large quantities. But so you can do oxidative additions very easily, and but then palladium is not the best guy, and so we moved to ruthenium and iridium for oxidation chemistry. But that's part of the story that I told yesterday, and now it's already 4 o'clock, so I shouldn't spend another hour telling you what we did with oxidation. So do we close it here? Are there things you'd like to know that I forgot to touch, or things that you'd like to know that may have been interesting? Now we could go for another 2 hours on carbene chemistry. I know I have a program at some point, so either you hate me because you don't dare to leave, or those guys hate me because I never show up. So maybe I stick to the program, no? So do you have any questions on carbene chemistry that we should discuss now? Do we close it here? So thanks for joining, and good luck with your research.